Hi, and welcome back to Statistics Online. Today we're talking about confidence intervals around the mean, and specifically we're talking about the case where we know the population standard deviation. All right, it's the common starting point to introduce confidence intervals. So some early intuition. So here's the deal: we don't know the average value, we don't know the mean from a population data set. So for an example, the IRS may want to know the average underreporting on tax forms. Okay, and they don't have this information. And to get at it, point two here, they estimate it by drawing a sample. Point three, they take that sample and calculate a sample mean. Okay, which is an average dollar amount, let's say, in the tax example, but an average of whatever value x is. And this is the point estimate. This is a single value, and it's a single numeric value that is considered our best guess about the population mean, mu. Recall that mu is the population mean. However, as statisticians, we don't just want to report that value and say, well, we don't know the population mean. We have x bar, this numeric value, and this is our best guess, because we know that x bar is random, right? It's a sample statistic that results from a certain sample size drawn from a population. Well, we could take that same sample size, but different observations, different people, whatever. In this case, the tax forms example would be different people. The different 1,000 people would get a different x bar. So x bar is random, and what we want to do through confidence intervals, okay, is try to structure how confident we are that our estimate is close. Okay, so we're going to put sort of a bounds, an upper and lower bound around our point estimate, and say, hey, we're 95%, we're 90%, we're 99% confident that the unknown value is between these two bounds. Here's another illustration of why we need confidence intervals. So mu here, the population mean, is unknown, hence the question mark. Genius! X bar is what we have. It's fixed. Okay, so here's the little animation. We don't know where mu is. We have x bar. We know x bar is random, so we're going to use our knowledge of sampling distributions, okay, and the normal distribution, and put an upper and lower bound on this thing. And at the end of the day, at the end of this video lecture, you're going to be able to form this interval and interpret it, and here's the interpretation. It's pretty simple. We are 95% confident, that's an example. The level of confidence is up to us. We are 95% confident that this interval is going to have a numeric upper and lower bound, contains the unknown population mean. Okay? Because we're going to work through our knowledge of sampling distributions, okay, from a previous lesson, and we realize that if this sampling distribution is normal, and our knowledge of the empirical rule and how the z-table works, okay, then we can calculate an upper and lower bound that we're 95% confident, okay, that this interval is going to contain the true value. All right, some early new notation in terms. We're going to introduce alpha today, and alpha is what we call the level of significance. All right, we'll be using this in our lessons on hypotheses testing and in regression analyses. But here, alpha, the level of significance, is going to be a value bounded by 0 and 1, so somewhere between 0 and 1. The confidence level is a percentage. Okay, so for confidence intervals, we typically speak in terms of confidence levels. All right. However, if you have a level of confidence or if you have a level of significance, okay, then you have enough information to tell me what the confidence level is or what the significance level is. So basically, you only need one. And so the level of confidence as a percentage is calculated as 1 minus alpha times 100, right? So for an example, if alpha is 0.05, if my level of significance is 5% or 0.05, then my level of confidence is 95%. All right. Another example is if I'm 80% confident, if my confidence level is 80%, then my alpha level of significance is 0.2. Okay, so if you have one of those values, then you can, of course, back out the other. We're going to begin today, and this lesson today, throughout, we assume that we know the population standard deviation. Okay, this is a stretch, because if you think about it, for any interesting case, when you don't know the population mean, and hence the reason you're constructing a confidence interval around your sample mean, it's a pretty far stretch to think that you would know the standard deviation of that population. However, this is what we call the simplest case, and then we'll move into the more slightly complex case in which we have to estimate the standard deviation of the population using S, which you may recall is the sample standard deviation. But for now, we're going to know sigma, population standard deviation. So constructing the interval. Here's the construction of the interval, the upper and lower bound. I have both of them up here. Though you only need to put one, they're symmetric. You can see that x bar is on the left-hand side of both equations, and then you have this z with this subscript alpha divided by 2, I'll talk about in a moment, times, hopefully you recognize this, sigma sub x bar is the standard error. That's the standard deviation of the sampling distribution for the mean. So x bar is the sample mean. That's our point estimate. Hopefully all of us could get there. That's adding up all your observations in your sample and dividing by n, the sample size. The standard error, again, has been introduced in the past. This is the standard deviation of the distribution of sample means. Z we've seen, but z with this particular subscript of alpha divided by 2 is new. Okay, when you see z with the subscript, again, this is a subscript. It's not telling you to multiply anything. It's information. It's saying that z value that goes in that equation is the one where alpha divided by 2, the area of alpha divided by 2 is to the right of that z. So anytime you see that notation, you say, okay, well, I need a z such that the area to the right of that z is alpha divided by 2. And if you commit that to memory, that's the only thing you need to commit to memory, because you know how to use the z table and you can progress in that fashion. The z values that we use in confidence intervals and later in hypothesis testing, we call these particular z values critical values. Okay, so it's a critical z value that you plop into that confidence interval formula. And that's it. And in fact, in a later slide, we'll see that this stuff that we're adding for the upper bound and subtracting in the lower bound from x bar is called the margin of error. It's half the width of this interval. And so that's really the only new part, is the margin of error. All I'm doing in this slide is isolating this new and important notation for critical value. So if you download these slides, you can look at it later. So what I want to do now is illustrate how to find these critical z values from the z table. In doing so, I'm going to look at this example. Okay, we're going to have a normal distribution, okay, a normal sampling distribution. And the question says, well, 95% of all sample means will fall within how many standard errors of the population mean? All right, now, if you look at this, and I say it's normal, you may think right away, go to the empirical rule and say, well, around 2 standard deviations, okay, approximately 2 standard deviations above and below the mean, we should see about 95% of the data. And that is true, okay? But I'm asking you to use the z table to get a more precise, up possibly to 4 decimal places, for that answer. It's going to be close to 2 by the empirical rule, but when constructing confidence intervals, when using critical values, we're going to use as precise an estimate as we can of these standard errors, of these z's. So let's do that now. All right, let's start with the normal distribution. And we're talking about a distribution of x bars, a sampling distribution, which we know is centered at the true mean. All right, And if we're looking at 95% confidence interval, we know, or confidence level, that we know alpha is 0.05. Okay? And 95% of the values around the mean, right, or an area of 0.95, that means that alpha divided by 2 is in each tail. Right? So this is alpha divided by 2. This is 0.025 over here, 0.025 over here. So 95% of these values are going to be in the interior of the table. Right? And alpha divided by 2 of these values will be in each tail. So if I'm looking for how many standard errors this is, in particular I'm looking for this z value, this critical value. I'm looking for the z such that the area alpha divided by 2 is to the right of it. So how do I use the table to do that? Well, we have to recognize how the table works. If I look up at a z value, the one that I need, right, it gives me everything to the left, right? It gives me the area in blue, but it also gives me this area over here in white that's left over. So 0.95 plus the 0.025, right? I want to look up a z that has a probability of 0.975, right? Because it's 0.95 plus the 0.025 is everything to the left. Because remember, I want everything to the right. So if I open my cumulative z table here, I'm in obviously the positive side of this distribution with positive z-scores. And now I'm looking on the interior of the table. I'm looking for 0.975. And you can see it right there. And that corresponds to 1.96. So the answer to my question here is 1.96. All right. The empirical rule says 2. The z-table says 1.96. That's the 1.96 is the one we're going to use in this in the construction of our confidence intervals. All right. And so this next slide proceeds in the same way. We just confirmed that the critical value for the 95% confidence interval is 1.96. It doesn't hurt to commit that to memory. Now, at the 90% confidence level, you should use the same approach and convince yourself that the critical value is between 1.64 and 1.65, and in this class we will use the average of the two and use 1.645. All right, and I encourage you to use this same method and find these remaining three, 85%, 80%, 95%, 75%. I should say that these three that I've highlighted here are, without a doubt, the most common critical z values you'll find, and so it doesn't hurt to commit those to memory. In the previous slide, I did just write out that 1.645 is the critical value for the 90% confidence interval. I'm walking you through it here. We know the answer has to be C. And let's look at why. So I'm finding 95% in the z-table. The reason, and the question says why, well, I know that alpha here is 0.1 and half alpha is 0.05, right? So the area to the right of the z value I'm looking for is 0.05. And so the remaining 1 minus 0.05 is 0.95. And again, you'll find that the z values are 1.64 or 1.65. When you're indifferent, take the average of the two. All right, so let's put it all together now. We have our point estimate, which is at the center of our confidence intervals. We have a lower bound. We have the upper bound. This was on the previous slide. So for the 95% confidence interval example, which is a very common one, we would have 1.96 as our critical value. and of course plus 1.96 times the standard error as our critical value. And finally, a new term or a new notation for this term, new notation and a new term. We have E, which is the margin of error, and E is simply that the combined term that you're adding to X bar and subtracting to X bar in the formation of the confidence interval. So E is Z times the standard error. All right, it's half the width of the confidence interval, you could think. All right, so anytime you see little e here, that's the margin of error. And the smaller the margin of error, the tighter the confidence interval around that sample mean. So a few remaining points here. The sample mean is random. X bar is a random draw from a population. Since X bar is random, then the confidence interval is also random, right? It's centered around a random variable. Moreover, the single confidence interval may or may not fall over the population value. We don't know, right? We've only calculated one sample, for instance, taken one sample, calculated one X bar, and we don't know if the interval is going to contain it or not. But we do know, this last part in bold, that whatever level of confidence we are, for instance, 95% of the intervals we create will fall over that population value. So if I'm 90% confident, then 90% of all the intervals I could create will fall over the population value. If I'm 80% confident, then 80% of all the values we could create will fall over the population value. All right? And so the higher level of confidence, all else equal, the wider the interval will have to be, because you have to be, for instance, 99% of all possible intervals will contain the true value. So, we previously determined that 95% of the sample means will fall between the values shown below on this graph, and that's 1.96 standard deviations away from the mean. You can see that 36 and 44 would be 2 standard deviations, and this area is slightly below those 2 standard deviations above and below the mean. Now, let's say I'm investigating 2 example sample means, one in blue, one in green. You can see that both of these sample means fall within that interval, and by that same notion, if I was to construct confidence intervals around these 2 sample statistics, those intervals would contain that population mean as well. And you can see that any X bar that happened to fall within these dotted gray barriers would result in intervals that contain that true mean. However, if I had a sample mean that fell somewhere lower than this 1.96 standard deviations below the mean, or higher, greater than 1.96 standard deviations above the mean, then that sample mean would consist of an interval that doesn't contain the true value. So, for instance, let's say our point estimate, our X bar is 35 pounds, right here. Will our 95% confidence interval fall over the true population value? And hopefully you can see that the answer is no. The answer is no, because the interval around 35 would be the same width as the interval around 40, and so that by that notion, it will not contain 40. So the answer is no. So finally, in terms of interpretation, the proper interpretation for the example of a 95% confidence level is that since 95% of all possible confidence intervals that we could draw or create for a certain size will contain the true mean, then we can say we are 95% confident that our particular interval, our particular numeric interval, contains the unknown population. So at the end of the day, you have an upper bound, lower bound, and you get to say, I'm 95% confident that this interval contains the unknown population parameter. So let's work through an example to finish up. So in an effort to estimate the average income in the state of North Carolina, let's say an undergraduate statistics student sampled 1,000 residents, okay, through survey methods, let's say. And that sample represents the population of interest and all that from Stats 1, or from previous lesson. She calculated a sample mean of $40,000. That's her X bar. And consider that the population standard deviation is known and known to be $1,250. And the question is, construct the 95% confidence interval around the sample mean. Meaning, what's the upper bound and the lower bound? All right? And so let's work through this. Just going to set up my drawing tablet here. Put some graphing lines in there. And we'll begin. We have recall a sample mean of $40,000, a standard deviation of $1,250, and a sample size of 1,000, and we are constructing the 95% confidence interval around our estimate. So, if you picture this, we need the upper and lower bound, and the lower bound is simply x bar minus e, and remember x bar minus e is the same thing as x bar minus 7 divided by, x bar minus z times the standard error, and I can write out this one more time. That the standard error, of course, is the standard deviation of the population divided by the square root of n. All right, and so that means that also the upper bound is going to be x bar plus my critical z value times the standard error. Right, and so now it's just about plugging in these values. We know that at the 95% confidence level, my z value is 1.96. We spent some time looking at that today. This is the 40,000. In both cases, of course, this is symmetric. And to calculate the standard error, we have 1250. And we have to plug in that square root of 1,000. All right, and of course, all right, and so what we see here is that when we do that, the margin of error, again, is $77.48. All right, and so the upper limit, excuse my penmanship as always, is the 40,077.48, and the lower is 40,000 minus that margin of error. Okay, and so at the end of the day, this is the answer to the problem. The interpretation is that we're 95% confident. I'm 95% confident that the unknown population mean income is between $40,077.48 and $39,922.52. So that concludes the lesson for today.